Now we're going to apply these steps that we learned for how to find and classify critical points for a pretty simple problem. Oops, dropping everything over here. So we're going to be asked to find and classify critical points of f equal to x 2x squared plus 2xy plus y squared minus 2x minus 2y plus 5. So I have a function that's given in terms of x and y only, no z's anywhere. So I know that I already have z equal to f of xy. Z's are gone from the equation, and I can calculate grad f. Remember, grad f is going to be partial derivatives with respect to x in the first component. So that's going to give me 4x plus 2y plus 0 minus 2 minus 0 plus 0. And then in the second component is going to be partial derivatives with respect to y. So it's going to be 0 plus 2x plus 2y. And for my 2x, my 2y, minus 0 minus 2 plus 0. And if you're still having trouble with partial derivatives, kind of maybe pause right here and make sure that you understand where all those different terms came from. Computing this gradient is going to be the first step for all these problems, so you really need to be able to do it. And I want to find the critical points by setting 0 equal to grad f. And so that means that I'm going to have, that 4x plus 2y minus 2, 2x plus 2y minus 2, the vector should be equal to 0, which means that I need 0 equal to 4x plus 2y minus 2, so that the first component is 0. And I need 0 equal to 2x plus 2y minus 2 at the same time. So I have a system of two equations with two unknowns. I know how to solve this. I'm going to start with the second equation because it looks a little bit easier. So 0 is equal to 2x plus 2y minus 2. That means 0 is equal to x plus y minus 2. That means y is equal to 2 minus x. Oops. Made a mistake right there. X plus y minus 1. So y is equal to 1 minus x. It's from that first equation. And then for my second equation, I've got 4x plus 2y minus 2 should be equal to 0. So I'm going to plug in what I know y is. I've got 4x plus 2 times 1 minus x minus 2 is equal to 0. Both the equations have to be true at the same time. Y equals 1 minus x tells me that the second equation is true. If I try to solve this equation with y equal to 1 minus x, I know that they'll both be true. So this gives me 4x plus 2 minus 2x minus 2 equals 0. So that's just 2x equals 0. So that's just x equals 0. So I know x should be equal to 0. Y is equal to 1 minus x is 1 minus 0. So I only found one point. X star, y star is equal to 0, 1. And that's a critical point. That's something that might be a maximum or a minimum, but I need to classify it before I know more. And I'm going to run out of space, so I'll go ahead and move this over to the next page. So I care about the point 0, 1. And I had my gradient 4x plus 2y minus 2. And 2x plus 2y minus 2. All right, and the reason I wanted the gradient over here is because that gave me f sub x and f sub y. So I need to compute. I'm over to my step 4, compute the discriminant. I already found my critical points, and this is the classification part. So I need d equal to f sub xx times f sub yy minus f sub xy squared. So f sub xx is the derivative of this with respect to x. 4x plus 2y minus 2. That's just 4. F sub yy is the derivative with respect to y of f sub y, 2x plus 2y minus 2. That's just going to give me 2. And then f sub xy is f sub x with a derivative with respect to y. So that's d dy of fx, 4x plus 2y minus 2. That's just going to give me 2. So my discriminant, fxx, fyy minus fxy squared, is just going to be 4 times 2 minus 2 squared. That's 8 minus 4 is 4, greater than 0. I just don't like that 0. So we're going to go and check what D means in a second. Real quick, I just want to warn you, I had told you that we would need to plug in x star, y star. This is just an especially simple problem. So we didn't need to plug in, I keep switching that, 0, 1, because D is constant. In general, you would be plugging in your D here in order to actually find a number that's greater than 0. There might be x's hanging around, and you would just plug in x equals 0. But when we find D, and we've plugged in our point, we check our 4 different conditions. And we're in these first 2 conditions where D is greater than 0. When that happens, we check f sub xx. And for us, we had fxx equal to 4, which is also greater than 0. So we're going to find that this is the point 0.01 is a relative minimum. And I'll go back and show you that that's what we wrote before. So if D is positive and the second derivative is positive, you're looking at a minimum. This can be kind of unintuitive to people, but remember that's the exact same way that it worked before when you learned it for 1D calculus. If you're looking at something that's shaped up like this, that means that your second derivative is positive, so it's a minimum. If you're looking something shaped downward like this, your second derivative is actually getting smaller, so it's a maximum. If you still have trouble with that, just come talk to me and we can kind of like, look at tangents and stuff and see why that's true. But for this specific problem, we're done. We found the critical points. There was only one, and we classified it. It was a relative minimum.